Hello class, so this is CSE 5250, Section 2, Week 6. Alright, so let's begin with a few clarifications from the last video because I felt like I didn't do a good job explaining how to set up MPI, nor did I do a good job explaining what was going on with the hello world function. So first off, let's clarify that. So, with the install instructions, when you go to this link here, it will take you to this Microsoft page that has download links for Microsoft MPI. This is Microsoft's implementation of MPI. What you also want, basically what you need to do is you need to download both of these. You need to download both of these, and you need to install both. Also for the instructions, I recently got a new laptop, so I had to do the installation myself, and realized there are a few nuances, such as, well, 32-bit versus 64-bit. So let's put this side by side, and we can compare them then. Alright. Alright, so when we go under Project Properties, if you're using Visual Studio 2022, the instructions are more or less the same. That's what I found out. But you have to pay attention over whether you're using. You have to pay attention over whether your project is configured for 32-bit, which is x86, or 64-bit, which is x64. So that's something you have to pay attention to, because if you select the 64-bit version, you're going to need the 64-bit version of MPI instead of the 32-bit version. That's just something to keep in mind. So what happens if you have the 64-bit version by mistake? Well, the thing is, you're gonna have to the thing is, a few files will be a little bit out of place, but they are there. So let's demonstrate that by setting my Visual Studio installation. Let's set this to 64-bit and see what happens. If we build this, we get a few unresolved external symbols. What that means, technically we have the wrong libraries. So for that, we have to go to Properties. Now, follow the instructions as you normally would for 32-bit. It's shown here. Go to C/C++. We want additional include directories, so okay, so wherever you installed MPI, the default location is going to be program files x86 / Microsoft SDKs / MPI. The include library is going to be the same because it includes both the x86 and x64 header files, I believe. So you just include the entire include folder, and that's the additional include directories. See, this is where it's gonna get different. So for the libraries, we go to linker, we go to here it is, additional library directories. We edit this, and again, pay attention to whether pay attention to whether Visual Studio is set to 32-bit or 64-bit. If it's 32-bit, that's x86. If it's 64-bit, that's x64. So you have to select the correct libraries. This is the library folder. So you need to select the correct one corresponding to whatever. You have to select the correct one, basically. So in my case, since I edit to 64-bit for the sake of demonstration, I have to select 64-bit. Right. And MS-MPI.lib, for that way you have to go to linker, input, and the last thing we type in is just MS-MPI.lib, and that's it. There we are. Now, hopefully if I build this, you can build it using Control-Shift-B. If we build it now, build succeeded. Nice. Alright, so the other little difference with using 64-bit, the 64-bit mode instead, is some of your files may be in a different location. I'll just show you how. Okay, so here we are in the project folder for this MPI project. If you just go to the debug folder, you have the 32-bit version of the executable in here. But if you have it set to the 64-bit version, you'll find an x64 folder here, and that has its own debug folder, and that has its own executable. So if you're on the 64-bit, if you're set to 64-bit by mistake and you're wondering where the executable is, you just basically, I'll just show it to you again. Right click the solution here, open folder in File Explorer. You'll see, if you're on the 32-bit version, you go to debug, and that's where your executable is. This is the 32-bit version. If you're on 64-bit instead, you look for the x64 folder. That will contain its own debug folder, and that will contain the x64 executable. Alright, so that's how we navigate through the folders to find the executable, because here's the thing, we need the executable to run the program. It won't work. It's not enough to just use the local Windows debugger here, because it's not enough to use the local Windows debugger because it's going to default to one process, and the point of MPI is to use multiple processes. Right, so I'm gonna pull up a PowerPoint slide showing a few bits of new content. Give me a second. Alright, so here I'm gonna explain better what's going on with the MPI function. No, the MPI sample program that I provided. And if you look on Canvas, I've provided a few more sample programs for you to try out. Some of them provided by me, some of them provided by my brother. So let's begin with this presentation. Okay, so remember back in operating systems, you were taught the idea of a process. A process is just a program in execution, and it has what's called a process control block that contains, among other things, a state of its memory and a state of its registers. Now, a computer will typically switch between processes multiple times a second, possibly thousands of times a second, and this is called context switching. It's what allows a computer to make it look like it's doing multiple things at once, especially when there's only one CPU core to go around. These days we have multiple core CPUs, such as my machine right now. Recall that my machine is an 8-core, Recall that my machine is an 8-core 16-thread. It's got an 8-core 16-thread CPU here, so it means I can execute up to 16 processes at any one time. Now, those processes could be related to one another, or they could just be standalone processes where each process thinks it has the entire computer to itself, because, in a way, each process really does think it has the entire computer to itself. However, you have situations where you need to have a process talk to another process. This is done through a process called inter-process communication, and there are two main ways for this to work. The first way is using shared memory, so each process has a section of memory that is designated as shared. So one process could write to that shared memory, and another process could write to the same section of shared memory. When you have something like that, you are introducing a few issues that can only ever be resolved using synchronization. So if one process is writing something at the same time as another process, basically you have problems there. At that point, you have to introduce something such as you have to enforce something called mutual exclusion to make sure that one process is not overriding the work of another process. It's like a parking lot. Only one car can ever be in a parking space at a time. Unless the cars are physically so small that you can just squeeze two of them in one space, but that kind of case generally doesn't happen all that much. So we enforce mutual exclusion by saying, hey, only one process is allowed into a section of shared memory at a time. And this works if you have processes on the same computer. What happens if you have a process that needs to talk to another process, but the two of them are on separate computers? Well, this is where we need to introduce message passing. And it's exactly what it sounds like. It's a setup where one process sends and receives messages from other processes. There was a rather noteworthy example of this. Recall back to the early days of the pandemic, and people were just cooped up in their houses with their computers, possibly bored out of their minds with nothing else to do. They hear about this program called Folding at Home. This is a piece of software, and it's specially designed such that if you have spare computing resources, you can donate those computing resources to Folding at Home. And what it basically does is it makes your computer a part of this virtual supercomputer network. And what this program does is protein folding for researching various diseases. Now, because of current events concerning 2020, so many people heard of this. So many people heard of this program and wanted to donate their computing resources to the effort of disease research. That at one point, Folding at Home, their entire network, at one point, was the most powerful supercomputer in the world. Yeah, wild stuff. And this can only happen if you have a message passing interface talking between separate computers that could be all over the world. So this is just one application of what MPI or what a message passing interface can do. So let's go back to our program. Now, I provided a Hello World program in the example code, and it's basically this on here. So this is the MPI Hello World program. We have a few variables called com size and rank. We also have a few more functions called MPI init, MPI com rank, MPI com size. After that, we have a print function that just says hello world but it also prints the rank and com size. And we have the finalize function. So com size is the number of processes to run. So if you're running 4 processes, your com size would be 4. It's however many processes you've set your program to run with. You can think of rank as a process ID. Back when we were looking at OpenMP, each thread had its own thread ID. Rank is basically rank plays the same role as that for MPI. So when I say rank and process ID, they're more or less the same thing. We also have to set up our main function so that it takes in arguments. So instead of int main, left parenthesis, right parenthesis, we have int main, int star argc, comma, character star argv. Now I mentioned the 4 MPI functions. The first 3 are needed to start an MPI program, and the last one is needed to clean up. It's basically to clean up the MPI environment once you're done with it. So MPI init is to initialize the environment in which MPI can run. MPI com rank is so a process can know what process ID it is. MPI com size is so that a process can know how many more processes there are. And as I said, MPI finalize is needed at the end of every MPI based program. So that's gonna clean up basically the entire environment. So once we're done, we are done. Once we save MPI finalized, we are done with MPI code. You can execute more code, but it cannot be more MPI code. Okay, so this is a really basic program, and it doesn't even feature message passing. Here, it's just gonna print out its rank and the number of other processes there are. So basically, each process knows there are other processes, but they have no way of talking to one another just yet. So what does it look like when we have message passing? Well, a simple example would be to have it such that rank 0 can send multiple. We can have it such that rank 0, that's the 0th process, rank 0 can send a message to all other processes, and then all other processes have to receive that message. So here we can use an if statement and a for loop for that. And here's what it would look like. This is the first half of the if statement. If rank equals 0, we can send a message to all other processes. Now the function for sending a message is MPI send, and there are 6 parameters. In this case, we're sending a string. So the first thing we need, in this example, the first thing we need is the address. Excuse me. The first thing we need is the address of the string. So for the first parameter, we can just pass in message.cstring here. The second parameter is the number of characters in the string. So for the second parameter, we can just pass in message.length. The third parameter is the data type. Here it's MPI.character. No, MPI underscore character. The rank of the receiver, that's the process ID of who's receiving. The last 2 parameters we can just set as 0 and MPI com world. The tag, those are the tag, which can be used to distinguish between different types of messages. And MPI com world, that's the handle to the communicator, but for our purposes, we can just set it to MPI com world. And this entire function is in a for loop that starts at 1 and ends at com size. This is because rank 0 is the sender. We have to start at 1 because here's the thing. You have to have every send in an MPI function have a corresponding receive. If you ever have a situation where you have a stray send or receive and it doesn't have its companion send or receive, you're gonna have deadlock and it's basically gonna keep the program from running properly at all. Another thing is you cannot send and receive to the same function. So if rank 0 were to send a message to itself, it's not gonna work. Okay, so this is the first half of the for loop. No, this is the first half of the if statement, and it contains a for loop that sends a message to rank 1 up to com size. So if com size is 4, it will send a message to rank 1, 2, and 3. And that's just the sender. For the receive, this is going to be the else section of the if statement. Here we're going to set it up such that we receive our message and put it in a character buffer of 14 characters. So if you look closely at the hello world message here, you'll notice that it's 13 characters. HELLO is 10 characters, world is 10 characters, but then you have to add a character for the space, the exclamation point, and the new line character. So that's 13 characters. So why is it 14? Well, this is due to the nature of C strings. They have to be terminated with a null. So the last character, so we have to have our buffer be one more character longer than the original message, and that final character is the null terminator. Now, the receive function is set up like this. There are 7 parameters this time. The first 6 more or less are the same, with a few slight differences. The first one is the first parameter is the address of the character buffer. The second parameter is the number of characters. The third parameter is the data type of what's being received. The fourth character is the rank of the sender. So who is this from? The fifth parameter is, we can just set it to 0. That's the tag from before. The sixth parameter is the handle to the communicator, which we can just set to MPI com world. And the seventh parameter, you can have a MPI status structure. It's called, the data type is MPI status. You can pass in you can pass in the pointer to an MPI status structure, and you can get a status message from that. But for our purposes, we can just ignore it and instead pass in MPI status ignore. And this is the receive function. And the rest of the program is just to print out that string. So with this in mind, can you imagine a situation where instead of sending a message, instead of one process sending messages to all other processes, we have it such that one process receives from all the other processes. Basically, you can do that too. We can also send all sorts of other data types, such as integers, floats, arrays of integers or floats. There's also an option for Boolean values that you can send. We'll play around with we're gonna play around with the program as well, so you'll get to see more of the programs in action. And if you want any more further reading, I have a few links here. One of them is two of these links are the send and receive function, and the other one is a cornell.edu link explaining a little bit more about the little bits of the parts of an MPI function. No, the parts of an MPI program. Right, so that's gonna be it for the presentation. Now, let's get back to playing around with MPI a little bit further. Right, so this is the you may have noticed that at the start of the video, I had this exact program shown here. And this is basically the same program from the PowerPoint slides. So let's try it out. So we debug it, right? Not quite. Remember, if you just use the debugger, it will default to single process execution. So instead, we have to go to where the executable is located. So here I have to build this. And remember, mine is set to 64-bit, so we want the 64-bit location. So open it. Okay, so right-click the solution and open folder in File Explorer. If you know you're on a 32-bit version, you just go to this debug folder here, as I mentioned a few times already. But we're on the 64-bit version instead, so double-click the x64 folder here. It has its own debug folder. Sorry. And there we have our executable. So how do we run this? Well, let's go to the let's click on the address bar here and just type in cmd. Now we've opened up a command prompt at the location of this folder. No, of this executable. So we also have the option of opening up PowerShell. So let's try that. Windows PowerShell is basically Windows' own implementation of a Linux-like terminal. So if I do ls, I can see all the files here, and one of them includes the executable. That's the executable that we want to run using command prompt. So cmd again, and this is the program we have to type in to run an MPI program. MPI exec-n. The third thing we have to type in is however many processes we want to run. So let's do 4 processes. And then the last thing we need to type in is the name of the executable. So for our case, it's CSE-5250 _MPI example program.exe. There we go. Now what's going on here? Well, process 2 is receiving a message from rank 0. And process 2 has received a message from rank 0 and it's hello world. We have the same thing going on with process 3, process 1, and rank 0 is just sending messages to all other processes. And once that's done, rank 0 will say it's finished sending messages. So that's basically what's going on in this section of code here. Let's try a few more example programs. Give me a minute. Alright, so I'm just gonna copy and paste another example program. One of this is provided by my brother, and I'll explain what's going on here as well. So remember the MPI init, com size, and rank functions? Turns out those have a return value, and that's basically an error code. So you can use that to your advantage for the sake of debugging, for example. So if something ever goes wrong, you can just, since these functions return a integer that's a error code, you can, for example, only execute certain code if that error code is MPI success. If you have any other errors, you can, for example, see what value I error is and see an entire list of error codes associated with MPI. So that's one thing you can do. Another thing you can do is you can explicitly state the number of processes that an MPI program is supposed to have. So here, we've basically hard-coded the program to be 2 processes exactly. And if it isn't 2 processes, if it isn't two processes, we can just abort the entire program. But suppose we've done all that and we have it such that the number of processes matches what we want. So what happens now? Here it's gonna be that if else statement from before, except we just have only one process. So rank 0, that's process 0, is going to send a message. This time it's an integer, 69. We're gonna send the number to process 1. So our MPI send function looks like this. First thing we have is the address of the number. The second thing we have is how many numbers. We only have one. Third is the data type. So we type in MPI int. Fourth is the rank of the receiver. So that's 1. And the fifth and sixth parameters we can just ignore. No. Not really ignore, but we can just set them to 0 and MPI com world. So rank 0 sends this number to rank 1. What's rank 1 doing? Well, here it is. First, rank 1 is going to initialize a value with which to receive the message from rank 0. So this is what the receive function looks like. And remember how I said that all these functions return an error code? Yeah, this is what I mean by that. So if something wrong happens here, if something wrong happens with the receive, we can save the value of the error code for later diagnostics, for example. So here's what the receive looks like. 7 parameters instead of 6. The first parameter is the address with which the address of the variable with which we're going to receive the message. So that's going to be the address of value. Next one is how many values are we getting? Again, that's 1. Data type, MPI int. Who is sending the message? That's rank 0. The fifth and sixth parameters are we can just set those to 0 and MPI com world. And the seventh parameter is this status here. So this is a struct. This is a struct, and we can take an instance of that struct and pass in the address of that instance, and we can get a status of what's going on here. So previously I had this set to MPI. I set this to ignore, so we didn't have to worry about this. But if you have a situation where you need to know the status, well, this is how you get it. Right. So with that in mind, if the error code reads MPI success, we can then print out the number that was sent to process 1, and if that didn't work, we can just say, oops, sending failed. And then once that's done, we just finalize the entire thing, and we return 0, and that's the end of the program. So what does this look like? Well, first we have to build the solution. And then we have to navigate to where in the folders does this executable live. So open in File Explorer, and since it's 64-bit here, we go to the 64-bit location, so it's x64, debug, and there's the executable. If I type in cmd into the address bar, I get the command prompt. So we can now type in the command, so mpi exec -n, 2 processes because it's asking for 2 processes, and then we can type in the name of the executables, which is CSE-5250 _MPI example program.exe, and there we go. Process 1 received value 69 from process 1 received value 69 from process 0. Process 0 sent value 69 to process 1. Nice. Now what happens if we didn't have two processes? Let's try this again. What? Oops. It's now 20 processes. Now what? Well, the entire program aborts. Alright. Alright, what else can we do? There is one other program, and it's kind of, in its a way, the opposite of the programs from my PowerPoint presentation. In that presentation, I had one process sending to all of the processes. Here, we have one process receiving from all of the processes. So here's how it works. For one thing, it's hard-coded, so you need to have at least two processes. But once that's done, here's how it works. If you are a process whose rank is not 0, you're going to send a message that's basically val times your rank. And this end function is set up as such. For the receive function, that's going to be for rank 0, and rank 0 is going to be receiving a message from all other processes. So we need to have a for loop that iterates from 1, the com size. We also need to have a variable with which to catch the received message. Maybe catch isn't the right word because try catch. We need a variable with which to receive the message. So for the receive function, we have the address of the variable with which to receive the incoming message. We have 1, which is how many numbers we're receiving. The data type, which is MPI double. Whoever was sending the message. So this is going to be I from this iterator here. This is going to be iterating from 1 to com size. So it's gonna, if it's 4 processes again, it's gonna be receiving from processes 1, 2, and 3. And then we can have 0, MPI com world, and status. So if the receive was a success, we can just print out the received value. And another thing that process 1 does, it's going to add up all the values that was received into the sum here. And then once it's received all the messages, it's going to print out that entire sum. And then we're going to finalize, and then we're going to return 0, and that's the end of the program. So what does this look like? Build solution. Yeah, this is going to be the same executable in the same location as before, so I can just reuse the same cmd.exe window to call up the program again by using the up arrow key. Let's do two processes for now and see what happens. Okay, so rank 0 process ID, this is rank 0. Receive the value -1. And our running total, it's just gonna, the running total is the sum of all the numbers sent from all the processes, and since there's only one process, that total is just -1. How about 20 processes? Right, there we go. Process 5 sent the value -5 to process 0. Process 4 sent -4. Process 6 sent -6. Yada yada yada. Process rank 0 received -1, -2, -3, all the way to -19, and it's gonna sum all those numbers and we're going to get negative 190 out of it. So that's the gist of how we can send and receive values from one process to another. So let's think about how we can translate this to the sieve of Eratosthenes. So give me a minute. Recall back a few weeks ago in one of the past presentations where I showed you how we can make the sieve of Eratosthenes and then how we can make it parallel. This is one of those sieves, but this is the open MP sieve. So how I had it, there's many ways to implement the sieve of Eratosthenes, but the way I've shown here is using two arrays. One array is just the entire list of numbers. The other array is just the other array is supposed to be a array of bools, but somehow it's in here. So here we have two for loops. The first for loop is to iterate through the entire array of numbers and picking out a number that is supposed to be prime. If you recall how the sieve of Eratosthenes works, it works by first crossing out 1, because 1 is neither prime nor composite. Then we go to the next number after that hasn't been crossed out, and so that's 2. So the outer for loop is iterating through the entire list of numbers. The inner for loop is iterating through that entire list again, but it's crossing out multiples of 2 that isn't 2. Once that's done, the outer for loop iterates to the next number that hasn't been crossed out, which is 3, and the inner for loop crosses out all the multiples of 3, and so on and so forth, until we reach the end of the list. So okay, so we have a bitmap that we use to denote numbers that we've already crossed out as non-prime. So again, this should be bool, but it's int for whatever reason. So and here's the thing. Processes have their own memory. And so nothing is shared between them. Unlike this multi-threaded sieve that uses OpenMP, the thing about a multi-threaded program is it has a lot of things that are shared between each thread. So threads have shared memory, among other things. So this is why we can just slap in a pragma here and then call it a day, because this for loop is going to be divided. It's going to be divided in such a way that each thread is going. Even if we divide up, even with this program, basically the code inside is accessing literally the same array here. If we're to implement this sieve using MPI, what we need to keep in mind is this. Each process is going to have its own memory. Each process is going to have its own version of the it's going to have its own version of the array of bools. So what this means is we need to set up MPI. We need to set up our program such that when we have the sieve operating, it's going to divide the work of the for loop among multiple processes, but each process has to eventually send back its copy of the bitmap back to another process that will take all those values, update them, and then send back the updated array of bools to all the other processes. What do I mean by that? So let's start with a really simple example where we have int. Let's say we have a bool. Yeah, let's say we have a bitmap, and it's hard-coded to be 10 values, and it's all true. True. Okay, so let's start off with just sending a copy of the bitmap from one process to all other processes. Then, yeah, we're gonna start off with having one process send a copy of the bitmap to all other processes. Each process modifies the bitmap in some way, and it sends those modified copies back to the sender. The sender then combines all those updated bitmaps into one updated bitmap, and eventually it sends all those back to all the other processes. So, first off, we're going to send a bitmap from one process to another process. So, if rank equals 0, if rank equals 0, and then we can populate, and then we can have an else here, and we can populate that later. For now, let's just okay, so let's copy this and put it in here, so that way yeah, we'll have it in here so we can, if I put it outside the if statement, every process is going to have its own copy of the bitmap, and I want to drive the point home that we want to send a copy of the bitmap from one process to all other processes. So, how do we send? With a for loop. So, for int I equals 1, I is less than tom size, I plus plus, and then we send. We need to send the address. For this to work, we need to send the address of the first element. So, ampersand bitmap 0. And then we have to tell the send command, we have to tell the send function that we're sending Boolean values. So it's MPI C bool. And that's the data type for Boolean values. The third data type, oh, actually that's the third data type. The second, no, that's the third parameter. The second parameter is supposed to be how many bools are we sending? That's 10. The fourth parameter is who is receiving this message. So that's going to be I because of that iterator. And the last two parameters are going to be 0 and MPI com world. And then we can just print out a statement that goes like this. So, rank 0 is sending a bitmap to all other processes. And then we can say rank 0 has finished sending a message. Has finished. Rank 0 has finished sending messages. So, that's rank 0. It's going to be the sender for all other processes. And this else here, this is for all other processes, so we need to have a similar bitmap with which to receive the message. So, bool bitmap receive, and this is also going to be a 10-element array. And we specify absolutely nothing else. What we've done is we basically designated a slot in memory with which to house a 10-element array of bools. So, how do we receive? With this. MPI receive ampersand bitmap receive 0 10 because we have 10 bools. Data type MPI C bool source is 0, tag is 0, MPI comworld for the 6th parameter. And we can just type in MPI status ignore for the 7th parameter. And yeah, that's gonna be it. That's what's needed to send. That's going to be all it takes to receive a message. So, to prove that we've received it, we can make another for loop that prints out the entire printed. That we can make another for loop that prints the entire bitmap. So, we can also say this. And this is just to say, oh, hey, I received something. So, for int I is less than 10 because our bitmap is only at 10 elements. I plus plus. And then we can just print out the bitmap. So, alright, so. And this is just one, and all of this is for one process to send a bitmap to all of the processes. So let's save this, build, and we try it out. We go back to command prompt here, and we call up the command for, let's do it with 4 processes. There we go. Rank 0 has sent a bitmap to all the other processes. And there we go. Rank 1 received the bitmap from rank 0. Rank 3 received the bitmap from rank 0. Rank 2 received the bitmap from rank 0. So now we have one process sending a bitmap to all of the processes. Now what? It's one thing for one message to send something to all of the processes. It's another thing for one process to receive that message, modify the data in it, and then send back that modified message back to the sender. So, let's do that. For our purposes, we just have whatever rank. For our purposes, we can just have it such that whatever rank a process is, that will be the index with which to replace a bit in the bitmap from true to false. So it basically looks like this. Bitmap receive. There we are. Right, so now we have it so that all of the processes is modifying the bitmap. So what does this look like now? Oh no, it wasn't. Let me reopen it. Right. CMD. Whoops. This is the wrong one. That's the wrong one. It should be the x64 folder. Debug. And try again. MPI is exec -n for processes, and there we go. There we go. Rank 2 has received the bitmap from rank 0, and then rank 2 modifies the bitmap so that the element with index 2 is flipped from 1 to 0. And we have a similar thing going on with all other processes, so rank 3 flips a bit at index 3, rank 1 flips a bit at index 1, and there we go. We can modify the code a little bit for the sake of neatness by printf \n, so all that appears on a new line. So now what? We want this information to be sent back we want the what's going on here? Yeah. Sorry, nothing. Alright, so every process has modified the bitmap, and now they have to send it back to the original. They have to send it back to rank 0. So we can do that by having all of the process send to process 0. So we can just copy the send function here and change some of the parameters. So instead of the address of bitmap 0, we have it be the bitmap received. We just have it be the address of bitmap received. And the receiver is going to be rank 0. And for the sake of demonstration, I'm just going to copy this and have it say rank has sent back the modified bitmap. Now if we run this as is, the program's not going to work, because now we have send functions that don't have a matching receive. So for the code in rank 0, we need to have another receive function. So, but this is going to be receiving from all the other processes, so we need to put that receive in a for loop. So I'll populate that soon enough, but what we also need is another, we need to store this new updated bitmap in its own buffer. So let's just call it bool bit. Alright, so for our purposes, we can just put that buffer in the for loop and have it be a 10 element array. Now, for this receive function, we need to have the address of the updated bitmap. No, the address of the variable with which to store the updated bitmap. So this is going to be the address of the first element. So then we have 10 because we have 10 elements. Data type is MPI C bool I as the sender, MPI 0 MPI com world, and then MPI status ignore. Now, because of how this is set up, it's going to be receiving the message, and then it's going to throw it away, and it's going to be lost forever. But we're going to reach a point where we're going to want to save that as well. So for now, let's just, at the very least, let's at least print out what the received message was. So we can add another for loop in here for int j equals 0, j is less than 10, j plus plus, and then we can similarly print each bit in the received bitmap. So we can also, just for the sake of readability, add another print statement here. Rank 0 has received modified bitmap from rank %d, and this is going to be the I of this for loop. This is a nested for loop. Build that and rerun it. CLS to clear, up arrow to re-enter the command, and let's see what happens. Rank 2 has received the bitmap from rank 0. Rank 2 has modified the bitmap, and rank 2 has sent back the modified bitmap. Okay, we're not quite there yet. Let's for the sake of readability, I kind of want to change this a little bit. So hang on here. Okay, so I'm just gonna print F a few end lines like that, and then rebuild and rerun. Rank 3 has received the bitmap from rank 0, rank 3 has modified the bitmap, and rank 3 has sent back the modified bitmap. And that's going to be true for ranks 0 and... No, that's going to be true for rank 2 and rank 1 as well. So what's going on with rank 0? You can see it here. Oh no, wait, something's wrong here. The receive isn't working actually. Hold on. Let me pause it, and I'll get back. Okay, I find the error. This is I, when it's supposed to be J. So, we'll rebuild that and rerun the program again, and it should work this time. There we are. So, rank 1 has received the bitmap from rank 0, and it's all ones. Rank 1 has modified the bitmap, we're replacing one of the bits with 0, and it's sent back the modified bitmap to rank 0. Meanwhile, this is the same with all other ranks. Rank 0 is sending a bitmap to all the other processes, and then it's going to receive a modified bitmap from all other processes. So each one of these is going to get a bitmap, and it's going to have one bit flip. But what we want to do is modify the bitmap such that wherever there is a 0 in any one position, wherever there's a 0 in any one position, we want that 0 to appear in the modified bitmap. Think of it like this. If we have in index 0, if there is a 0 anywhere, the modified bitmap will just be 0. If it's all ones, then the value in that new bitmap will just be 1. So we can accomplish this by using an AND operation. Here's how. We can do this by modifying this for loop even further. So it's not just receiving the updated bitmap, it's going to update this bitmap. So now this bitmap is going to be updated. So here's how. Bitmap I update the bitmap with updated values. So bitmap I equals bitmap I and bitmap updated I. Actually, no, it's not I, it's J. I don't want to make that same mistake again. And then as a final step, we can print out what the modified, what the updated bitmap looks like. So if we rebuild that, now remember, we're updating. We are updating the bitmaps in such a way where if there is a 0 in any one position, it's going to appear as a 0 in the updated bitmap. So if we AND this, and this, it's going to be 1. If we AND this, and this, it's going to be 0. This, and this is 0, 0. This, and this is 0. And everything else is going to be 1. So the resulting updated bitmap should be 1, 3 zeros, and then 1s. Is this what we get? Okay, so there's some of the code is out of place, but that's an easy fix. Actually, this code should be right outside the for loop. So I space that there. There we are. Let me just get all the code indented properly. So, as a recap, rank 0 is sending a bitmap to all other processes. All other processes is going to receive that bitmap, modify 1 bit, and send back the modified bitmap back to rank 0. Rank 0 is going to receive all those modified bitmaps and combine them into an updated bitmap at the end. So, let's build this one last time. The video is a bit long, but it's all essential to understand how we can conceptualize a MPI sieve. So, with that, did it work? Ah, yes, it worked. Let's just ignore all the other processes. Let's ignore all other processes because we know what they're doing by now. Rank 0 is sending a bitmap to all other processes, and it's going to be a bitmap where every value is true. Rank 0 is going to receive a modified bitmap from each process, and it's going to combine all of those bitmaps into an updated bitmap such that it's going to be bitmap and bitmap and bitmap. We're ANDing the values from each bitmap into one modified bitmap, so wherever there's a 0 here, it's going to show up here. So 1 0 0 0 1 1 1 1 1 1, and that right there is our updated bitmap. If you can imagine how we can implement this into the sieve of Eratosthenes, you can imagine having this process of sending bitmaps and receiving them and then updating them in a for loop. So eventually, we want all of this to be in a for loop, and that's going to be the outer for loop of the sieve of Eratosthenes. Yeah, it's going to be in the outer for loop of the sieve of Eratosthenes. For here, we're going to need, for here, instead of this modification of 1 bit in the bitmap, we're going to have it such that it's going to be in another for loop where, yeah, this operation is going to correspond to the inner for loop of the sieve of Eratosthenes. This updating, the sending and receiving and updating of bitmaps is going to be part of the outer for loop of the sieve of Eratosthenes. So eventually, what we want to do is rewrite the sieve of Eratosthenes using MPI, where it has all of this sends and receives going on. You also have to keep in mind that when we parallelize the sieve this way, that we don't accidentally have each sieve doing the same work over and over again. What we want to do is divide the work among multiple processes such that one sieve is getting one process is getting a fraction of the work of the sieve of the inner for loop, but cumulatively, all those processes are doing all the sieving action as required by the sieve. This is just the first step in getting the MPI sieve to work. I'll just say right now, this may take quite a bit of time just to get it to work. And that's why I did not assign a due date for the MPI sieve just yet. So, try this out. If you have any questions, let me know. And you can also try all the other programs that I've shown here. And then next week we'll pick up from here and try to build up the sieve. Try to build up the sieve this way using MPI, and we'll take it from there. And then we'll talk about benchmarking the two sieves later on. I'm not gonna require. I probably won't require you to write an NVIDIA CUDA sieve. Rather, I'll just show you what a completed NVIDIA CUDA sieve would look like instead. So, the first 4 main assignments it's actually going to be 3 now. So, it's going to be the sieve by itself, no parallelization, and then 2 more sieves using OpenMP and MPI. And that's going to be it for this week. Again, if you have any questions, let me know, and I'll see you next week.